Well, welcome to the review session. The pattern I think would be reasonable to do is if you have questions already, at this point, please bring them up, and I'll try to order them in what seems like kind of a logical progression, so we don't have to go back and forth, say. And then we'll just go through your questions in a systematic way, I hope. If not, I'll talk about things. Trying to help prepare. So, some thoughts of what we should talk about here? Yes? Parallel and series circuits in general, capacitors and resistors? The relative brightness of bulbs when you add resistors. That goes back to series and parallel resistors. In a way, it could actually apply to capacitors too, but I don't know that they talk much about that in your notes. Okay, so that's a very good subject. So, okay. Any other topics you think worth talking about? Yes, sir.
It's like a specific problem from one of your past experiments.
Fine.
A charged object on a capacitor plate.
Yes.
So the charged object is positive, but it's on...
Let me see if I remember the problem. Thanks.
Number 3.
Large plates are attached to a hollow metal ball. Charge is held inside the capacitor. May I take this with me? Yeah. Let me. Okay. Okay, this is a problem that involves the ball is then released. What's the force on the ball? What's the velocity? What is the kinetic energy? Change in potential, change in potential energy. Yeah, that's a nice set of problems. Good.
I specifically have a question about
the change in potential energy?
No, just change in potential voltage.
Yeah.
Is it negative because the positively charged object is on the positive plate, so it's going against?
The change in potential? Yes, it's starting out. Well, let me. This is one of the. This would be early on in this logical series, so I'll try to answer that on the way. Okay. Any other thoughts? Yes, ma'am.
Could we cover electric potential for continuous charge distributions?
Sure. Yes. That's a good one. Yes.
Maybe an example problem like work on a dipole?
Dipoles. Okay. Electric dipoles, of course. Yes. Okay. Well, those seem to be about electric fields and potentials. Fields and potentials. I think that's the general category we're dealing with here, including dipoles. And what was the one? Yes, there. What
electric potentials for
continuous. Yes. And I think this problem here, there's test problem would probably follow this test problem. What year was this? 2012. Okay. Any else think you want to add in? Yes, sir.
In one of your slides, you explained the Van de Graaff generator. It ends by saying that a flame would be attracted to the Van de Graaff generator.
A what would be?
A flame.
Flame?
Yes.
Did I say that?
Oh, you can't.
Wow.
I'm just not sure what the logic is behind that.
Why that would be? A flame attracted to the Van de Graaff generator. Okay, let's see if I can figure that out by the end of the day. Well, it sounds to me like, roughly speaking, probably the flame is ions in the flame, and probably the Van de Graaff, it being charged up, is going to attract some ions. Because, roughly speaking, I would guess. But that may well appear in here. Yes?
I know we have series and parallel listed, but could you explain why after the capacitor has been going for a while,
Yes.
why at the end the current will go zero?
Oh, that's now a capacitor, series and parallel. I think what the gentleman first asked for was a series resistors. But you're now asking about capacitors. Capacitors. Acting as a battery, is it the basic idea?
Yeah. The difference between when you immediately close the switch and then after it's been closed for a while.
Okay. So that would come under the fancy words of charging and discharging capacitors? Well, this is going to be a challenge because we're going to be going over the whole course in 40 minutes. All of good questions, though. Okay. Let me try to be brief. First thing is electric fields and potentials. Well, the electric field refers to, there we're trying to represent forces. And so they're connected with forces. And therefore they are intrinsically vectors. The electric field is what you get when you take the force per unit charge. That's the basic idea. You're starting with a force, and you want the amount of force per unit charge. And these are vectors. Now, let's maybe illustrate that with the problem you brought up. The question is, we have a large parallel plate capacitor. So it looks like something like this. Metal plates, conducting plates. Plates are 4 meters apart in a vacuum. Its plates are attached to a 16-volt battery. A hollow metal ball of small radius and mass of 160 grams, charged to 2 coulombs, is held inside next to the positive plate. Let's say this is positive, say. And we're going to put a positive little ball over here of 2 coulombs. The ball is then released. Okay. Now, we could answer the question about the charging of the capacitor at this point. We could say, that's maybe we'll do that afterwards. But, there is an issue of how the capacitor gets charged. And we have something on Do you want to hear that first? I mean, should we go through this in very slow steps? Maybe so, because we didn't emphasize. I talked about this in our last two lectures. But, so, what is happening when you attach that 16-volt battery to this set of plates, these big plates like this? Well, this battery has an electromotive force, meaning it's trying to push charge out of the battery to wherever it can go. Now, if you attach it to these plates, physically what's going to happen is the electrons are going to come out of the battery and run onto this plate because they can get away from the battery. And the battery's pushing them out. When they do that, electrons are going to run out of this plate because they see these electrons over here. So they're going to run here. So literally, that's what's going to happen. Okay, now this, in a sense, takes a finite time. Chances are there's some resistance in the circuit, even in the battery or in the wires, which we normally forget, but for this purpose, we may want to remember it. Okay, so what is actually happening here? We have the capacitor, and you see, there is this EMF over here. The voltage on the capacitor is given by Q over C, because the definition of capacity is the amount of charge you store for the voltage you put on the capacitor. Again, capacity has the feeling of a storage thing. You're storing charge. And the more charge you store, the larger the capacity of the thing. So if you get more charge for the same voltage, you say it has more capacity. So the word actually helps a little bit in this case. And if you jiggle the formula around, you can see that the voltage is proportional to the charge. In other words, this capacitor has no voltage on it if there's no charge on it. It's an open circuit. It's just a plain two plates with air in between, or nothing in between, so it's an insulating space, so it's no current, no voltage, nothing. But if you start putting charge on, namely the electrons start to run, this gets negative, this gets positive, so charge starts to accumulate on the plates. So if I were to draw the picture of that, I would say that, let's see, I want to make three drawings. Let me make them one above the other so that we'll see it as a function of time what's going to happen here. So at first, the voltage is, when I just connect the circuit and I allow the electrons to move across, there's no charge on the capacitor to start with. So let me put that first. Q is 0 to start with. Let's say I start at this time t equals 0. And I close the switch. The charge starts out at 0, and it increases. The charge on, say, the plus plate. In other words, I chase electrons away from here, and the positive charge accumulates on the plus plate. Now, because of the law that I just wrote here, that the voltage is equal to Q over C, now that I'm putting charge on that plate, a voltage is on this plate. So at the same time, the voltage follows in proportion, just as this equation says. The voltage goes up. How far does it go up? Well, it can only go up to when this voltage here is equal to voltage here, because then it's pushing back. And if this voltage is equal to that voltage, the current has to stop. Because why should I go one way or the other? The voltage is the same. So the voltage goes up to the EMF that I put on that the battery pushes. So the voltage rises to here. And the Q stops at the voltage of the EMF times whatever that capacitor is, right, by this equation. So what I do is I rise up in Q up to the EMF that's on the battery, which is something, times the capacitor, which is determined by the shape of this thing. The capacitor is the area over the, it's a geometrical thing with a little stuff inside. Okay, so that's the way Q goes. V follows in proportion. But let's also put down the current to the plus plate of the capacitor, say. When I turn on the switch, well, what happens is the current jumps up because it sees, the electrons see a place to run. So they jump up, and then it dies down. Right? Actually, so at the beginning, this capacitor is actually looking like an open circuit. It's a very good conductor, and the current jumps up at the first instance at t equals 0 here. What does it jump up to? Well, it jumps up to, if there's a little resistance in the circuit, which there always must be something, it'll jump up to the EMF over R, whatever R is in the circuit. This is getting beyond what I actually told you before, but all I really want you to know is that the initial thing it will do is jump up because the electrons have now a place to go. They can go onto this plate. And so it'll jump up and load the plate with charge. Does that make sense? I hope so. Yes? That's right. You basically have an open circuit, and the current goes to 0, because an open circuit, the current will not flow. The current to that plate will not flow. So it goes, yes, very good point. So it's going from here, it's acting as a short circuit. In other words, the current is as high as it can be. The only limit is the little resistance that's in the circuit. The capacitor itself offers no resistance. It's getting a little bit beyond what I expect of you, but the point is that at this point, this is a short circuit, and the capacitor itself is offering no resistance. The only thing that limits the current is this kind of resistance that's in the circuit. These guys here. There may be a little stray resistance in the circuit, or you could put a resistor in the circuit. You probably should. And then after a while, after a long time, way long time, the current goes to 0 to the capacitor, which is saying that the capacitor here is an open circuit, which it really in nature is. In the long term, it's charged up. Its voltage is, it has a voltage on it, but it has no current. And if it has no current, we would say that if the current is 0, the current is sort of the voltage over the resistance. If the current is 0, we would say that the resistance is infinite. So we would say that over a long time, the capacitor is acting as an open circuit. That's what you said, did you not? That's correct. So it starts out looking like a wire, a short circuit, lets anything through. If you do it fast enough, you get through the capacitor. But after a while, it acts like its real self, which is an open circuit. But you can surprise it and get through a capacitor. Inductors are the other way. You can't surprise an inductor. If you do a quick jump with an inductor, it'll fight you back. It's a choke on a fast thing. But if you wait your time, inductor will let you through. But we don't worry about inductors right now, but just for... So this is what happens in that first stage, okay? Now, on the... So, okay, let's be logical here. Let's say, okay, now we know what we did, how to charge that capacitor. It's charged up. It's got charge on it now, and it's got a voltage across it. Let me get that homework problem again. This is actually very nice. I wish I had done this in the first. I hope this is clearer than perhaps my first time through this. But it's nice to do this. Okay, so now we have the condition of charged up capacitor, and we know how we got there. There was a sudden burst of current. Current flowed. Total amount of charge went on these capacitors. The charge that went on is all the current that flowed times the time, because current is equal to the rate of change of charge with time. So the current, see here, the current flowed for a certain amount of time, charge built up, and then steadied. The current went to zero, we're adding no more. The charge levels off, because I'm not adding any more after a certain time. Does that make sense? So that all hangs together. Stop me if you don't get it, because this is, speak now or forever hold your peace. Yes, sir.
So current that eventually goes to zero, that's current zero.
It's the current, yes, it's the current. I'm trying to make the distinction, the current going into the plus plate, as it were. Because there's current in the whole circuit except through the capacitor itself, which is an open circuit. We're going to modify that one. Maxwell modified that a little bit. But no real current, no electrons move through the insulating gap. So yes, this is the current in the whole circuit. It's the electrons running down here. That's the current. And there's electrons running over here. That's a real current too. So there's this current going to here while it's going, charging up the capacitor, filling up the bucket, and there's current coming out of the other side. Well, those are electrons. Those are electrons going. Actually, the current is the other way. Oh, that's another tricky thing, of course. The current is actually this way. That's the velocity of the electrons. I'm sorry, guys. Yeah. Because we have this business of the electrons going one way and the current the other. So literally, the electrons are going one way. The current is going that way, going into the battery. So the current is actually that way. Sorry, we have that distinction, okay. I wanted to be careful because somebody in the office hour raised the question of what's actually moving. It's the electrons. So the electrons literally are coming out of the battery, landing on this plate, chasing away electrons this way. That's the electrons. But a convention is that it's the positive, it's the opposite of the way the negatives go. So the current is going the other way. And that is the current in the wires, but not through the capacitor itself, because that's an insulator. So that's your open circuit. And it jumps up. So actually, the net charge on the capacitor is zero, because you have plus and minus at equal amounts. So if somebody asks you, what's the charge on the capacitor? You could be a wise guy and say zero, no matter what, because there's always plus and always minus. Or you could say, well, I really mean the charge on the plate of the capacitor. That's what this is. This is charge on one plate, right? Because there's equal and opposite charge on each plate. So when we have this formula, we're really talking about charge on one plate. Okay, moving along, this is actually a very illustrative example. So this is an interesting point, and you can see it in this diagram where the current jumps up, charge starts to accumulate. Then as the current drops down, the charge accumulates slower until when the current is zero, the charge stops changing. It's like pouring water. At first you pour it very fast and then slower, and the bucket fills up, and then if you stop pouring, the bucket stays to a certain amount, a certain quantity. That makes sense, hopefully. more or less? Okay, let's try to move on. So in any case, now we come to this homework exam problem. What is the force on the ball? Now, I've given you some information here. A 16 volt on the plates. I already said that. And 4 meters apart. Okay, now we want to find a force on this ball when placed in this capacitor near the plus wall. Okay? Yeah. I think we can do it right here. Well, that's an important formula. So we're trying to get the force. And we're given the charge on this object, and so the force is equal to the charge times the electric field. So we're given the charge, we have to find the electric field. Now the electric field, somebody have an idea what that is? Given the 16 volts here and 4 meters apart. They're the symptoms of this problem. The electric field is equal to the voltage over the difference of this distance between the plates. So the electric field is equal to 16 volts over 4 meters. So it's 4 volts per meter. And then we find the force by simply taking 2 coulombs on the charge times the electric field, 4 volts per meter. And I would say that the force is going to be 8 newtons. Yes? That's right. That would apply in a parallel plate. Very good question. The more general thing is that the electric field is a very important one. Let's put that up. That's a major equation. It's actually equal to the negative of the rate of change derivative of v with respect to a distance. So it's the rate of change, which in the case of when v is when E is constant, or when V is, see here, V is, in this case, V is just lines like this. dV dx is equal to, in this special case, is equal to V over the separation. This is for parallel plates. That's why we love them so much, is that it's simple. But in general, it's the derivative. So, for example, for a point charge, this is a very good question, where the potential lines are like that, your electric field is given by the gradient dV dx, or VdR, maybe in the case of a point. It's the rate of change of the potential as you approach the thing. But in a capacitor, it's that simple formula. Okay? Okay, so that's the first part. What is the velocity of the ball? Now, you could do this 2 different ways. So we got the force easily enough, hopefully enough. Now, the next question is, what is the velocity of the ball when it reaches a negative plate? Well, you could use either force or energy. We have these 2 methods. By force, you could say, let's see, we're asking for the velocity. So I want the final velocity, and I know the force. And so the final velocity is simply going to be the acceleration. Let's see. The symptoms of this, we know the distance. We know, from the first part, we know the force. And if you know the force, then you know the acceleration. It's equal to F over m by Newton's second law. So we know the acceleration from this. And we have the formula that the final velocity squared is the initial velocity squared plus 2 times the acceleration times the distance, which is sometimes I call s. The initial velocity is 0. The acceleration is F over m. And the distance is our 4 meters. From putting, you can put in the force, whatever that was it not 8 something? Newtons. And the mass was given here as 160 grams. That's 0.16 kilograms. So you can see where I can get 2F and then times 4. So that would be one way of doing it using force. Or you can use potential. Knowing that the potential difference is 16 volts, you can say, you can use the energy conservation that the initial kinetic energy plus the initial potential energy initially is equal to the final KE plus PE. Final. Kinetic energy originally is 0, but its potential energy is 16 volts times the charge. That's the voltage, so we have to get the potential energy is the potential times the charge, which is 2, and equals kinetic energy at the end, which is the unknown, and the potential energy at the end we're going to call 0 because we've used up whatever potential energy. The difference is what counts. And the difference is 16 volts. So I have to put that then equal to the final kinetic energy, which is a half mv squared, and I end up with the formula v squared is equal to 2 times 16 times 2, 32, divided by the mass. Now, does that come out the same? Square root. Square root on both sides. Yes, me. Yeah, v squared. So if I want v, I would take the square root. And they look remarkably the same, don't they? You got 2 times 32 is 64. And here I've got 2 times 8 is 16 times 4, which is 64. So I have 64 over 16.16. So they are the same. You have 2 different ways of doing it. And miraculously, or thanks to physics, they come out the same. Okay, that's nice. Okay, kinetic energy of the ball. Oh, the velocity. And the kinetic energy. Well, we've got the kinetic energy here, too. What? This 32?
Yeah, because you said potential is 32, right?
The potential is 6. Potential energy, yeah. Okay, let's see. The potential energy to start with is high. The potential energy is high. When the plus ball is near a plus plate, its potential energy is high. Because in fact, it's going to move. It's going to get out of there. So it's really plus potential energy to start with, 0 potential energy at the end of this, and it's all gone into the kinetic energy. So that signs even come out right. If you get a negative sign for velocity squared, you're in trouble. You check again, because square root of a negative number would be imaginary and you'd be trouble. Yeah, okay. Is that okay? Yeah. Okay, change in potential of the ball is minus 16 volts. The change in potential energy of the ball is, plus it would be potential energy has also decreased by to 32 joules. Yes, sir? The change in the potential, it's gone from 16 to 0. So the change is minus 16.
So does that mean if the charged object
Yeah, if it were down here, it would have no potential energy because it's already, if a plus ball is already right next to the negative thing, it's as happy as it can be. Only when you push it next to a positive plate, you give it potential and you make it unhappy, it wants to run away.
So like, it's minus because it wants to go to the
That's right. It's lost potential by going from close to the plus plate to close to the minus plate. So it's lost its potential. It potentially could do something when it's next to the plus plate, but it loses it by the time it gets to the negative plate. Because get that feeling of potential and potential energy. It had potential energy there. So that's I think, the answer to that, more or less. Now we have 15 more minutes or so. I don't think we're going to be chased out of here. If you guys want to hang around even longer, we could. But let me keep plunging on here. So maybe that answers enough about fields, forces, potentials, potential energies. Hopefully. It's a good problem, good illustrative problem. Yes, sir? Is Kirchhoff's laws what? Well, that's an interesting question. A lot of people ask that. See, Kirchhoff's laws are general, but in the book, they tend to apply them to these multi-loop circuits, which we are not responsible for. Because then if you have a multi-loop circuit, you have to put in Kirchhoff's laws, as I say, in their full glory, loop after loop after loop. And that requires simultaneous equations and a lot of math, but you don't learn too much. So, but Kirchhoff's laws also apply to series and parallel circuits, which we're going to get to here. That's all I really care you to know, how to do a series and parallel. But the laws apply, because if you go around the loop, you're going to get zero total voltage around the loop. That's Kirchhoff's law. The current going into a node will be conserved. That's Kirchhoff's law. Except that it's simple in the case of... You don't have to know those bridge circuits and all that. You could do it if you had to, but you don't have to. Okay. Yeah. Yes, question.
You already answered it, but when you're looking at the White's negative, can't you just say because it's going from the positive to the negative, it's final minus initial, therefore it's going to be negative? Isn't that for Y, the potential is going to be negative 16? That's what I'm saying.
Say it again, please.
Starting from the positive side, going to the negative side.
You mean the current? You're talking about the current?
Yes. So it's final minus initial, and it's going from the positive into the negative. So it's just going to be negative.
I'm not exactly sure what you're talking about. What's going from positive to negative? Current? Voltage? What?
Well, the current is going from the positive side of the battery.
Yes,
to the negative side of the battery.
that's correct.
So therefore, the potential energy is just going to be the final, which is negative.
Yeah, well... I think we're getting into a complication here. Here, current is going to go from positive, the conventional current in the battery is going to, or from the battery into this circuit, is going to go from plus to minus. That's one.
No, I got that. What I'm saying.
Well, yeah. Now, then we go to his problem. Namely, I put a charge inside that object. It's already charged up. Right. Now, I put that charge in here. It's already charged up. I'm not, and it's kind of like the source of the external field. Then the question is, how does this charge behave? And it's going to go from high potential to low potential, and it's going to pick up speed. It's going to gain speed. In so doing, it's going to give up potential energy and gain kinetic energy. And it's going to go away from the positive toward the negative. It's like two different problems. See, I didn't have to know that to start this problem. In fact, so all I'm saying is I have this situation where there's a positive plate and a negative plate. I didn't tell you how I got that. That's how I got it. But once I got it, I put a positive charge here, and it will move according to the potential difference between those plates. Does that make sense? Yeah, okay, good. All right, we have a few more minutes here. I think we're down to series and parallel circuits, maybe? There was a question of the discharging of the capacitor. Do you really want to see that, too? The discharging works the same sort of way. I could maybe expropriate this diagram and do a similar thing here. I don't know if it's worth it, though. Your discharging situation is now here. You can't do it quite the way it is. You need another resistor, it turns out, to really understand this. Suppose this, now I'm using this as just a loaded capacitor, charged up capacitor. And the good question was, what happens when I discharge it suddenly? So that means that I've done this action, I had the circuit closed, current flowed, negative electrons being the ones that are moving, and so on. But the current flow, and it's sitting here for a long time. So I start out, let me put the same thing, Q, V, and I of the capacitor. And I'm saying, I've been sitting there for a long time. The Q has been sitting on that capacitor a long time. And at a certain time, I open the circuit. Then what happens? I'll go over it very quickly. Clearly, if this is open, the battery is gone. The charge is here, this charge here. They have a path to go through this resistor to get back to each other. The thing that was preventing that before was that this battery was putting as much voltage on this as the voltage in the capacitor itself, so that the current couldn't change after a while in the capacitor. But once you open it at, say, some time, big T, then the charge can run through this resistor to the negative side. So it will, and it's going to drop like a shot, like that. And of course, because V is proportional to Q, V is going to follow it in its exact same shape. Now, what do we say about the current? Well, we said that capacitors let sudden things go through it quickly. Capacitors, for fast things, are shorts. So what's going to happen is that it's going to quickly shoot down and go back up. It's going to act like a short to the sudden change, and what's going to happen is the charge is going to run through here to this plate, through the resistor, and the charge will dissipate. The net charge on that positive plate will go to zero, and its voltage will go to zero because there's no charge on it, and the current will suddenly change, and then gradually as the charge goes away, the current will go away. Does that make sense? Pardon, dear? Oh, well, I'm using the idea that when I put current in the first place, I had my blue chalk, the current was going into the capacitor that way. It's because the current is going to be coming out the other way. See, I put current in. This is the conventional current going in this way, if you want to put an arrow on it. When I discharge it, the current is going to come out that way. It's going to go this way, right? Because this is plus. This side was plus. So the current going out will be that way. So it's sort of the opposite sense. And you sort of it sort of makes sense because on the one hand, I put current in, and in the other way, I'm taking current out. So just to be finicky, I just made them the opposite signs. So the total current over the life of this cycle is current went in, and now current goes out. Those are details I didn't go over in class, but somebody asked for it, and you got it right between the eyes. Sorry about that. So let me quickly do... That's the whole story on capacitors, and there's a similar story on inductors. You just go through the whole schmear over again. But does that sort of make a little sense? Yeah. You can copy it down, and I don't know when you're going to use it exactly, but let's hope sometime. Let's see. But that's the story. And so you just want to remember that a capacitor is always acting like a capacitor, and a resistor always acting like a resistor. See, a resistor, again, it's a little, I shouldn't go into that, but in a resistor, it will always do its thing, which is to say the current and the voltage will always be in step. Here, the current and the voltage look different because it's a funny thing. It depends on temperature. Not temperature, but time. In a capacitor, things vary with time. And but in a resistor, you'll always have the current and the voltage proportional. In a capacitor, the voltage and the charge are in step. See, the voltage and the charge. In a capacitor, the voltage and the current would be in step, and they are different here. So all of that really hangs together. Now, series resistors, the point being that if you have a certain voltage, whether it be alternating or DC, you have, if the things are in series, then the same current passes through both, because it's sort of a Kirchhoff law. When the current going into a junction has to be the current coming out. On the other hand, if you have a parallel circuit, something like this, when the current comes to a junction like this, it has to split, and the sum of the two currents going out is equal to the sum of the currents coming in. Now, the point is that you will have in resistive circuits the current times, let's say, R1, R2, and R3. The voltage drop across this, going from plus to minus, will be I times R1. That's the I in branch 1. But you'll have current going in branch 2 here, I in R2. And you'll have current going in branch 3. And they divide up here. The lower the resistance, the more the current that will flow. The potential is the voltage drop across these things is the same. The voltage on R and 2 and 3 is the same because these wires have the same, are equal potentials. So the potential is the same here. So that's what you really want to know. The point is, the bulb that will light brightest is the one that has the most current, which is the one that has the least resistance. That's the trick. Are you okay? Did I say something wrong? It can happen. I don't know how deeply you want to go into this, but this is the main point, that you just, the sum of the voltages around here must be equal to the EMF. That's a Kirchhoff law that somebody asked about. Yes, it applies, but we can just break this down by combining parallel resistors by the law 1 over R equivalent is equal to the reciprocals of the different components of the parallel part. So we just break this down into one equivalent resistor in series with this, we find the voltage drop across each. And the one that carries the most current is the one that is the brightest. That's because the power in it is I squared R. Well, you'd have to actually make sure that you have to maximize I square and R. So it can be a little bit trickier than saying the current is the most. Also, R has to be multiplied into the I squared. So that's what tells you brightness. Power used is equal to brightness. Pardon me, sir? It will depend. It will depend. It depends on its resistance. You'd really have to figure, if that had a very low resistance, very little voltage would drop across it, and very little power would be used in it. So you'd really have to see just what the values are. Now, often in these problems, they say 3 equivalent lamps. Oh, then we could probably do it, yeah. If all the R's were the same, yes, that simplifies the story. And I think, yes, this would be the brightest because it has the same resistance, but all the current is flowing through that one, whereas part of them are going through this. So right offhand, if all the bulbs were equal, you could jump to that conclusion correctly, that since these share the current, the current through them must be lower, and their resistance, by definition, is the same. You can say that immediately, if these were all equal, this guy would be the brightest. And these, in fact, would share the current equally. They would be 4 times dimmer, in a way, or 4 times less power. Because I would be less, and I squared would be 4 times less. I don't know where you go more with that. Yes? Tested on the demonstrations. Well, I think what you'll find is that my problems are mixtures of things. Oh, this is maybe a point I should make. Don't be overwhelmed if the problem looks complex. The chances are each little part is simple. Just do the simple parts, and in a way, in principle, yes, you're asked to know the demonstrations, but they're also just part of all of this. They just illustrate these very points. And you will... I know that there was one test time I put in the Van de Graaff, and we were talking about it in office hour with the belt outside versus the belt inside and all that. Yeah, that's a very direct allusion to the demos. But in a way, what I'd like to do is hide the idea that, yes, you've actually seen this in a demo, but not quite the way I state it. But if you realize the analogy or the nearness to what you've seen, the reason I do that is because, you see, in real life, you won't always be presented with a textbook symptom. In real life, the symptoms are always hidden and in some other context. But you have to ferret out what is the symptom. And have I seen this symptom